Hello all, myself Sabina Devi, Assistant Professor, Department of Physics. In this video, I am going to explain about Schrodinger wave equation, time-dependent wave equation. Okay. So in previous video, I explained about the properties of matter waves and physical significance of wave nature. So in previous video I explained that what is meant by matter waves, right? So matter waves are nothing but every material particle associated with a wave nature is called as matter waves or de Broglie waves, right? So now, we in previous video also itself I explained about the applications of matter waves. So it will be used in the application part time independent Schrodinger equation. So we have used psi function in Schrodinger equation, right? Okay. So in this video I am going to explain about the Schrodinger equation. So Schrodinger equation is nothing but it is the one of the basic equation in quantum mechanics. Okay. So we have two types of Schrodinger equation. One is time independent Schrodinger equation, other one is time dependent Schrodinger equation. Okay. So in this video I am going to explain about the time independent Schrodinger equation. So the time independent Schrodinger equation is the cornerstone of quantum mechanics. So describing the stationary states of the system. Stationary states are those where the probability density of the particle does not change with time, right? So this occurs when the potential energy is time independent, right? So next one, introduction. So what is quantum mechanics? So the theory governing the behavior of the matter and energy at the atomic and subatomic level. So deals with the probability and wave particle duality. We are well known about the quantum mechanics, right? Okay. So we know that the duality. Okay. So every particle has wave nature as well as the material nature. So this is called as the duality. Okay. So in quantum mechanics, so it explains the probability and wave particle duality. Okay. The Schrodinger equation, the central equation of the quantum, this is the basic equation in quantum mechanics. This is the central equation of the quantum mechanics. So it has two main forms. One is dependent equation and time independent equation. So the focus is time dependent Schrodinger equation. So why time independent Schrodinger equation? So describing the evolution and the beyond stationary state and the examples. Okay. So describing evolution, the time dependent Schrodinger equation describes how the quantum state of a system changes over a time. So essential for understanding the dynamic processes. Okay. So the beyond the stationary states, the time independent Schrodinger equation describes the stationary states. At that time it has constant energy. So the time dependent equation is needed for the systems that are changing with time. So the interacting with the field. These are all the examples: scattering experiment, atomic transitions, and the molecular dynamics. So these are all the time dependent equations examples. So the derivation. So now we start with the total energy. So we know that energy is equivalent to kinetic energy plus potential energy. So in the quantum mechanics operators, so energy operator E bar is equal to I h cross dou psi by dou t. So momentum operator P is equal to minus I h cross del. So substitute into the classical equation energy equation. So replace the classical variables with the corresponding operators, so that we have to apply the wave function psi of r comma t. So I h cross dou psi by dou t is equivalent to h psi. So E psi is equivalent to h psi. That is called as time dependent Schrodinger equation. So h is the Hamiltonian operator that is equivalent to I h cross dou by dou t. So E is equivalent to minus I h cross del. So I h cross dou by dou t, that is the energy operator. Okay. So that starts with total energy and go to the quantum mechanical operators and substitute in the classical energy equation and apply to the wave function psi of r comma t. Then finally we will get the time dependent Schrodinger equation. So the time dependent Schrodinger equation I h cross dou psi by dou t is equivalent to h psi of r comma t. So psi of r comma t is nothing but time dependent wave function describe the state of the system. So h cross reduce the Planck's constant, h cross equal to h by 2 pi, and h is the Hamiltonian operator. So the interpretation is the equation related to the time evolution of the wave function to the Hamiltonian operator. Next one is Hamiltonian operator. H is equal to minus h cross square by 2m into del square plus v of r comma t, that is equal to Hamiltonian operator. So minus h cross square by 2m del square is the kinetic energy of the operator. So v is the potential energy of the operator. So solving the TDSE. So TDSE is nothing but time-dependent Schrödinger equation. So general solution, find the analytical solution is often difficult to impossible. So analytical solutions, the possible for simple potential, the free particle, numerical methods and approximation methods, we have used time-dependent Schrödinger equation. And computational tools also we have used time-dependent Schrödinger equation. Software packages like MATLAB, Python. So here we are using time-dependent Schrödinger equation. So separation of variables in special cases. So v of r comma t. So r is nothing but the position and t is the time. So simply we can write v of r, that is time independent potential. So that time we will get the solution. Psi of r comma t is equal to psi of r comma e power minus I e t by h cross. So these are the applications of time-dependent Schrödinger equation. So the applications are atomic and molecular physics, condensed matter physics, and quantum chemistry and quantum computing. These are all the applications of TDSE. So this is the example for the time-dependent Schrödinger equation. So summary, in this video I explained about what is meant by time-dependent Schrödinger equation. And describe the time evolution of the quantum system. So it is essential for understanding the dynamic processes. So solving the TDSE can be challenging, but various methods can exist. So it has wide-ranging applications in various fields of physics and chemistry. Thank you all.